Well, that's good. Right. But it's good that there's that connection with industry, because that's what we need. Also, the French connection is still there. And do the French people come out and teach?
I can feel from feel the drop flowing. So usually the first little
you met already. Oh, I see. So they get accepted. They get paid. That's a good thing. Actually, who funds it anyway? I like
No. I haven't done yours yet. Somehow I got an email from saying that he's going to finalize. That means that's not. We got an angry email from Noel for that.
Yeah, it's our special cups. Yeah, like, you get a picture of your whole just get one. Anybody can go and get their click there. Well, no.
He already managed to get into the Monday on June. Before Friday. So, yeah. 12 meaning Monday to sorry. I also that was
So I actually have there is a guest list, like the Eventbrite guest list, and I didn't bother to print it out. I just threatened people that if they didn't sign up, they might be kicked out of the room. But how would I actually do this? So if you, hi, how you doing? Yeah, exactly. So what do I do if actually we get to a point where some people show up and says, we booked. What do I do? You think so? You think so? I have to just ask anybody knows who they are. We have to rely on people, being 5 minutes. I could warn them. Just speak clearly. I think. Let me just ask I did have the anatomy lecture where there was 264 seats and an old wooden machine. You know, very rickety. But I
No, I saw your email. No, because I'm leaving when we're going to from Malaysia.
well, I mean, of course, you know, that's the danger, right? You stream it and then you come here and there's nobody here. It's like just this one here. No, I left one for myself. Not that one, that's mine. There is actually video streaming into the room over here, experimental video streaming into the room down here. So you might prefer that. This one is taken. There's video streaming in the room down here. It's new here. We're just learning about it. So it's a great pleasure to have Martin Heyer here. He's, I think everybody knows Martin Heyer, and he's been speaking here many times, although not at the Bay Center yet. This is the first time. So he's obviously a fixture in the UK mathematical scene. I actually knew him before a long time ago, indirectly, because I read a paper with his father ages ago. But yeah, it's just a wonderful pleasure to have you here to talk about the universality and probability theory.
Thank you very much. Thanks for the invite. First time in this building, very nice setup. So I assume that sort of the majority of the audience is not probabilists. Is that a fair assumption? Okay, good. So maybe if I start with basics. So in probability, so sometimes when you tell, especially say non-mathematicians, that you're a probabilist, then they tell, oh yeah, so you know who's going to win the next World Cup or something like that. Obviously you don't. And because we, as probabilists, we can sort of compute probabilities, but then actually we can't really. The thing we can really do is actually transform probabilities. Right? You can sort of know that assuming this and that, then you say, well, the probability that this or that happens is maybe the sum of the two probabilities if they're disjoint events and stuff like that. So you have a number of rules that allow you to transform probabilities. And so you still want to assign probabilities to events somehow to start with, right, before you can transform them. And so there's essentially two ways of doing that. So the first one, which you're all familiar with, is symmetry. It's, the standard example is you roll a die, there's sort of 6 possible outcomes, and you're in a situation where you can distinguish between these 6 possible outcomes, right, because you just look at the die. But the mechanism that produces the outcomes doesn't really distinguish with them, right? Assuming that the die is sort of balanced and that the holes aren't too influential on how it moves, the mechanics of throwing the die essentially don't see which way it's oriented, and so there are 6 possible outcomes. You can distinguish them. The mechanism that produces them cannot. And so basically the only reasonable way of assigning probabilities to them is to say that they're all equal, and so they all have to be 1/6. Or the even simplest example is the coin toss, with the same story with 2 possible outcomes. But then there's a more sophisticated mechanism, which is what I want to talk about in this lecture, which is universality. And so most of you know one instance of universality, which is the central limit theorem, right? So the central limit theorem tells you that if you add up sort of more or less independent random variables, and they don't have to be completely independent, and they're all sort of more or less the same size, but they don't have to be exactly the same size, and then you look at the outcome, you get something random, but that something random is always going to be distributed according to something that looks a bit like a Gaussian distribution if you have sufficiently many things that you add up. Right? So for example, here one thing you can do is you can do like you toss a coin 100 times, so you get an outcome which is a number between 0 and 100. You just count how many heads you get. And then you do the statistics of that. So you do 1,000 runs of these 100 coin tosses. And then you say, well, sometimes you get 50, sometimes you get 51, sometimes you get 49, and you count how many times you got 51, how many times you got 49, etc. And you get some sort of statistic like that. If you do 10,000, it looks already more like a smooth curve. If you do 100,000, they basically align here on that smooth curve, which is the Gaussian distribution. Right? Now, what I want to talk about today is sort of instances of this universality. So that if you want the broad sort of mechanism here, right? The idea is to say that if you have a random outcome that is produced by sort of many different random inputs, then very often the outcome, or sort of the probability distribution of the outcome, doesn't really depend too much of the details of the inputs. And it also often doesn't even depend too much of the details of the transformation that produces the output from the input, as long as it's sort of within a certain class. And so the first example of that, which I want to talk about, is Brownian motion. And so that was discovered actually by Egenhuis in 1780, but then also by Brown in the 1820s. And so what they did was the following sort of experiment is, well, so in the case of Brown, he was a botanist, so he was actually looking at sort of grains of pollen, or even, it wasn't actually pollen, it was some sort of little things inside the pollen that were suspended in water, and he was looking at that under a microscope. And what he was seeing is something like that, right? So you see these little particles, and they kind of move around in an erratic way. And he was wondering, you know, why do they move around like that? So in the beginning, he thought these things are maybe alive, and then realized pretty quickly that they weren't. And he made sure that the water itself wasn't moving now. And then, of course, the explanation that people later came up with was that, of course, water is made up of molecules, and if it's a non-zero temperature, these molecules actually bounce around a bit like billiard balls. And so you have many of these little billiard balls bouncing around. You have these very large particles at the scale of the water molecules that sort of sit in the middle. Every time they get hit by a molecule, well, they change their velocity a little bit. They sort of move a bit in one direction or the other. Now, of course, each molecule has a completely negligible effect on that huge particle, but there's many, many, many of them, and they kick it, you know, very, very fast. And what you see is sort of the aggregate effect of all these water molecules sort of bouncing on these pollen grains. And so at the time, so it wasn't completely clear, you know, that was the right explanation, right? Because in the 1800s, it wasn't clear that matter is made of atoms. And so actually, well, so let me just go back towards so there's two bits now. There's, on the one hand, you want the sort of physical explanation for the phenomenon, and on the other hand, you want some kind of mathematical description of the phenomenon, right? So this guy here, Fourier, he was involved in the mathematical description, although he actually lived before Brown's discovery of Brownian motion. Well, he was sort of an interesting guy, right? So he was actually in Egypt. I think he was actually running the Egyptian Museum in Cairo for a year or something like that, and he also worked as a politician, so he was a prefect for 15 years. But mathematically, he's mostly known for two things. On the one hand, he's known for Fourier transforms, which is that you can sort of write any signal as a superposition of pure waves, and that's used if you want to compress sound or something. For example, MP3 is based on that. And the other thing he's known for is Fourier's law. And so Fourier's law is basically the heat equation, right? So he's interested in the propagation of heat. And he said, well, if you want to model, if you want how heat propagates in a solid, essentially that's described by the heat equation of dTu equal to the Laplacian in space of u, where u is the heat profile as a function of space and time. Now, what does that have to do with Brownian motion? Well, the idea is that you can describe, you know, take one of these little pollen particles, and now, you know, you look at it under the microscope, you see that some given location at a given instant of time, and now you close your eyes for a few seconds, and you try to guess where that particle is. Now, of course, you can't predict because it sort of moves around in an erratic way, but you can predict the probability of, you know, where you can find it, so the probability distribution of where you find that pollen particle, right? So you know that it's not going to go very, very far, and you know that it's not so likely that it stays exactly still. So you have some description of, you can imagine that you could derive some description of that probability distribution. It turns out that this probability distribution is actually described by the heat equation. Okay? The same as the one that describes sort of the spreading of heat in a solid. And so actually it was, so Einstein and Smoluchowski, so they really came up with the proper explanation, if you want, of Brownian motion in the early 1900s. And not only with the sort of qualitative explanation, but actually with the quantitative explanation. Okay, which allowed you to sort of assuming, because so at the time the situation was that the sort of atomistic hypothesis, so the fact that matter is made of atoms, was reasonably well accepted, right? So it was sort of the preferred theory, if you want. But people didn't have sort of like one killer experiment that wouldn't be explained in any other way, right? So there were always sort of funny other theories, with ether or whatever, that people could use to explain whatever you'd see. And the point here was that Einstein and Smoluchowski, they came up with, so at the time people already knew sort of Avogadro's number, so like the number of, so like assuming that matter is made up of molecules, they kind of knew what the Avogadro number is. And using that, Einstein and Smoluchowski actually computed, if you want, the diffusion coefficient of these grains of pollen in the liquid as a function of the diameter of the grain of pollen, the viscosity of the liquid, the temperature, and so on. And so they came up with a kind of formula for that diffusion, and then you can actually just check that experimentally. Because it's not easy to check, because you need sort of like little, very, very small grains or something that you have in your liquid that are sort of very much the same size. Right? So if you just throw little grains of pollen where you've got tons of them, then they're all slightly different sizes, and it's difficult to do reliable statistics on that. And actually, Perrin, a few years later, did that, and he got the Nobel Prize for that. And that was really the experiment that sort of settled the debate concerning the existence of atoms. Now, interestingly, sort of just a few years earlier, Bachelier, who's another French guy, he submitted his, well, that's the only picture you find of him in the internet. I'm not even 100% sure it's really him. That's the only picture I found. So he submits his thesis in 1900, so it was 5 years before. And he was interested in something completely different. So he was interested in sort of explaining the prices on the stock market. Right? But the explanation he came up with was pretty much the same as the explanation of what made the grains of pollen move. Right? Except that what plays the role of the grain of pollen now is the stock price, and what plays the role of the water molecule is sort of people on the market buying and selling shares. Right? So the idea is to say, well, you have a company, maybe the market value of the company is £1 billion. Now, since there are probably no billionaires in this room, you might own sort of, maybe a few hundred or a few £1,000 worth of stock in that company. Now you sell your stock, well, £1,000 is nothing compared to $1 billion, right? So it's not really going to affect the price of the company or anything, but it's going to affect it slightly. Now, if many of you sort of decide to sell your holdings at the same time, that's going to drive the price down, because there's going to be sort of an oversupply of the stock. And conversely, if all of you decide to buy from that same company at the same time, well, it's going to drive the price up a little bit, right? And so it's more or less the same kind of mechanism. And so he as well somehow came up, with the conclusion that actually, if you wanted to describe the probabilities of what the stock price does, well, at least, some very basic model is to actually use the heat equation for that. And so that was, in some sense, that's kind of the foundations of black holes, for which they got the Nobel Prize 70 years later. And he didn't even get a job out of it. Well, because what happens is he got a job at the Sorbonne, but then the World War I broke out, and so then he lost his job. He had to actually go to the war, and then by the time he came back, the job wasn't there anymore, and the sort of establishment French probabilists, people like Stephen Beauty and so on, and so you shouldn't use mathematics to sort of describe something as low as stock prices and stuff like that. And so they really didn't like his work, and so he never got a job in Paris. So he worked for many years as basically a math tutor. In the end, he got a job when he was in his 50s or so. And that was, I don't remember where it was, maybe in Bordeaux or somewhere. It wasn't in Paris. But, well, anyway, so nowadays he's considered the founder of mathematical finance. But at the time it didn't do him any good. Now, mathematically, so we've seen that somehow the heat equation comes into the game here, in the sense that it tells you how these probabilities somehow spread, the probability of seeing, say, that grain of pollen at a given location at a given time. But then what you'd actually like is somehow a more hands-on mathematical object. You would want to have an object that actually really describes the trajectories of these particles, or like the actual trajectories of stock prices that you sort of see if you open the Wall Street Journal or something like that. And so this was actually done by Wiener, he was also kind of an interesting guy. So he's of course very well known in probability because of that construction of what's now called Wiener measure. But he did many things, and he was very interested in robotics. He actually invented the word cybernetics. And he was also interested quite a lot in sort of signal processing and noise suppression, noise filtering. So there's a Wiener filter in digital signal processing, which is the same Wiener. In particular, if you probably know the company Bose that produces these headphones and stuff. So that Bose, who founded that company, was actually Wiener's PhD student. So what Wiener did here is that he managed to, if you want, build a probability measure on the space of continuous functions, which sort of describes Brownian motion. Right? And so what you see is now it's a real mathematical object that describes these kind of curves. Right? So it's a probability measure on the space of continuous function. So if you draw a continuous function randomly from that probability measure, it typically looks like that. Okay? And the construction of the measure is related to the heat equation. So it has the property that if you sort of look at where the curve is at a given instant of time, and then assume that you only know that and don't know what it does later on, then the probability of seeing it somewhere at a later instant of time is given by the solution to the heat equation. And then Donska somehow in the 50s, so he showed that Brownian motion is somewhat universal. So we've seen this universal character already in the fact that the same mathematical object shows up to describe the grains of pollen suspended in water, or the evolution of the stock market, right? Which a priori you see sort of the idea is that the mechanisms, sort of the story that you make about the mechanism is somewhat the same, right? But of course the actual details are completely different. And that's the idea about this notion of universality. Somehow like two systems that are sort of described by the same high-level story tend to produce similar outcomes, even if the actual details are very, very different. So they've built this Brownian motion. So this Brownian motion, you can also view it as something like that, right? Sort of the simplest way of getting Brownian motion is the following way: is you start say you start at 0, and then at every, say, integer times, you decide whether you go up or down. And so you just go either up by 1 or you go down by 1. You sort of draw a random step function like this. And if you take a random step function like that, and then you sort of squash it down, you say, well, this should really be a very short amount of time, so you make it epsilon. And then the correct way of scaling things here is to say this should be about square root of epsilon. Then if you send epsilon to 0, this actually converges to a random curve, and that's Brownian motion. Now, you can ask yourself, can you do a two-dimensional analog of that? Right? So in the sense that here there's time is one-dimensional. And so you can do a natural two-dimensional, and that would be the following. So I replace time by a grid, like this hexagonal grid or a square grid or something like that. Here for this construction I have to have a bipartite one, so one that you can color with two colors in such a way that each guy always has only neighbors from the opposite color. So that's a bipartite grid like that. And now the analog of this construction would be to look at a function which goes from that grid to the integers, which has the property that for any two neighboring points on the grid, the values differ by exactly +1 or -1. Okay, so if the value of the function here is, say, 10, at these points it has to be either 9 or 11, right, etc. And so then you can do the same thing, right? So this would be this is the one-dimensional analog of that. And so as here, you could just say, well, I look at all possible functions like that, and then I just pick one at random. I take them all with the same probability. I pick one at random, and then I ask myself, what does the thing that I pick look like if I look at what happens at very large scales? Right? So if I sort of zoom out to the extent that I sort of blur the details of that grid, I'm only interested in what happens at very large scales, what does it actually look like? And although it sounds like a very similar problem to the construction of Brownian motion, that's actually much, much harder. The left is an actual simulation of a grid like that, of size, 1,000 times 1,000 or so, and you draw one of these random functions, and then you color it sort of darker when it's higher and brighter when it's lower. And the picture on the right is a picture of the object that you're supposed to get in the limit. And here, the object that you're supposed to get in the limit is something called the free field. So it's described by Gaussian distributions, a bit like in the central limit theorem, and also a bit like Brownian motion is completely described in terms of Gaussian distributions. And well, since it's described by Gaussian distribution, it's completely determined by its covariance, which is just a logarithm here. But actually, even in simple cases, so even in the case where the grid is simply the square grid, right, there's no proof this is true. So there are some models for which people can prove that. So here I put a few names. There are many more people who worked on these kind of problems. And so even this somehow very simple generalization of Brownian motion, you're already getting to things where things aren't really known and there's current research going on. So you know the answer at least, or at least we believe that we know the answer, but there are only special cases in which one has an actual theorem. Now in both examples here, still the thing that you get is there are some sort of central limit theorems, right? They are kind of more complicated forms of central limit theorem, but still so proving this is like proving some kind of central limit theorem, because you still get Gaussian distributions in the limit, even though they're very strongly correlated. But then there are other interesting models where you don't expect to see something like the central limit theorem. So here's one model which is sort of a model of phase. It's like the simplest toy model of a phase transition. And so the way the model works here is the following. So you take a grid, so a square grid again, and now at every point of the grid, you have a number which is either +1 or 0 or -1. Okay, so think of this as being, so it's like a spin model somehow, and the spin can either point up or down at every point of this grid. And then, unlike in the previous situation, so in the previous situations we had sort of some kind of constraints, and then we just said, well, we just pick one configuration at random, and then we see what we get. So here, instead of picking, if you just take configurations like that and you pick one at random, it's not terribly interesting what you see, right? So you see sort of half of the guys are going to be up, roughly half of the guys are going to be down, and it's not going to have much structure somehow. So the interesting thing here is to not pick things sort of uniformly at random, but to pick them with a probability which is proportional to a quantity like this. Right? So what you do here is you look at all possible neighbors, so all possible pairs of neighbors, okay, in your grid. And then for each pair of neighbors, you multiply the two spins. So basically, you see, what is this? So it's basically 1 if they have the same sign, and it's -1 if they have opposite signs. Okay? And that parameter beta here is positive. So this exponential is going to be big if many of them are aligned, right? Or if neighbors tend to be aligned. And it's going to be very small if neighbors tend to not be aligned, right? So like the typical configuration under the uniform probability is going to have very, very small probability under this measure, right? Because if you take just a typical completely random configuration, you know, there's going to be pluses and minuses just completely randomly, and so neighbors are typically not going to be aligned. Well, maybe half of them are going to be aligned and half of them are not. Which is going to come with a very, very small weight here. Whereas, for example, the configuration where all of them are aligned, well, that one would come with a very high weight, but there's only one such configuration. Right? So there's kind of the trade-off between the weight that configurations come with and sort of how many configurations of that type there are, right? So when they're all aligned, that comes with a very high weight, but there's very few of them. And the ones that are sort of completely disordered, they come with a very low weight, but there's many of them. Right? So it's not completely clear how this balances up. And that actually depends on the value of that parameter. Okay, and so what you see, depending on the value, is typically either, so if the value of the parameter is large, which corresponds to small temperatures, so beta is like 1 over temperature in statistical mechanics. So at small temperatures, you see something like this, which is that basically the energy wins, so the mechanism that have these things tend to be aligned wins. And what you tend to see is that most of them are aligned, and then there's a few outliers. So here you see mostly yellow, and then there's a few black inside. Whereas at high temperature, which corresponds to small values of beta, you see more like something like this, which is completely dissolved, right? So here you see basically about the same number of blacks and yellows, and they're all just sort of more or less independent. Of course, you see, if you look at small scales here, you see that there tend to be sort of dark regions and light regions. So locally, they do tend to be aligned somehow, but there's like a typical sort of length scale. So there's a typical length scale here, which is about that, so that they tend to be aligned when you look at that scale, but if you look at larger scales, it looks completely disordered. And then there's a critical value somewhere in between, and that's the interesting one. Right? So that at the critical value, these two mechanisms have exactly somehow the same strength. And so what you see is a sort of complicated fractal kind of picture, right? Where you have sort of dark regions and light regions, but both are sort of infinite size in one, right? So there's as much light as there is dark, but they are not, I mean, it's not like here where they're sort of mixed in a rather homogeneous way, right? So you have these sort of very interesting fractal structures at large scales. And so you can ask yourself, do you have, you know, is there a sort of continuum object that describes this here? And so that was, well, so it was conjectured sort of back in the 80s, I suppose by Tardy, who was a physicist at Oxford. And then there was a proof very recently, I think about maybe 4 or 5 years ago, by a number of people. Chuck Newman, Christophe Galban, and a number of collaborators, who actually constructed, if you want, that object. So it's like the limit of that object if you sort of zoom out and you look at it from very, very far away. So there is a limiting object, but that object is much harder to describe. So it's not Gaussian anymore. So you cannot describe it just in terms of Gaussian distributions or simplify its covariance. And again, it's conjectured to be somewhat universal. There's absolutely no proof. Right, so what do I mean by this? It's in the sense that if you take pretty much any model which has the same kind of features, right, in the sense that it would have the same dimension. So here this picture is two-dimensional, the construction is two-dimensional. So if you take any sort of two-dimensional model of this type, where you have configurations, you have two different states or two different phases, and you have this kind of competition between energy and entropy, and you put yourself sort of just at the point in which energetic and entropic effects are kind of the same, you expect to see exactly the same object when you zoom out to very large scales. Okay, but nobody has any clue on how to prove that. Now, so we've seen that you have these different situations in which you have sort of random objects. There are sort of universal continuum sort of random object that describes sort of the large scale behavior of some random models. And so you can ask yourself, so what are the sort of properties of these things? So in general, they are not Gaussian. So the first few examples that I showed you, the Brownian motion and the free field, so they were Gaussian. In general, they are not. One thing is that they're always somehow scale invariant, because you're interested in describing what happens somehow at very large scale. So it's some kind of limit under the operation of zooming out. And so if you manage to get a non-trivial limit, then that limit itself has to be invariant under the operation of zooming out, right? Since it was obtained by taking a limit under zooming out. So they would have to have some scale invariance, some kind of self-similarity, so on. Well, in many cases you expect some rotation invariance, but that's not clear. So for example, you see, so the examples that I showed you, they are not themselves rotation invariant, right? Because they are defined, say, on a square grid or hexagonal grid or something, so it's maybe invariant under rotation by 90 degrees, but it's not invariant under rotation by 15 degrees. In the limit at the critical points, you expect some sense influences to come from all scales, and so you expect the effect of these sort of the grid to be washed out. So you do in general you do expect rotation invariance. So then, since you expect scale invariance and rotation invariance, it's quite reasonable to expect conformal invariance, which is you want sort of the local analog of rotation and scale invariance. And that buys you a lot in two dimensions. And then all of the examples that I showed you, and many examples where people know how to analyze things, they are local in certain sense, right? So for example, in that Ising model, sort of the model with the plus-minus spins, the interaction was very local. You just looked at neighbors and you checked on whether they were aligned or not, right? That's a very local thing, quantity. Here also, in some sense, everything is purely local. Somehow, if you know the curve up to this point, right, you just decide either you go up one step or down one step, and it doesn't depend on what happened before, right? It just depends on where you are. So these models are defined in a very local way, and so you expect that in the limit, well, that locality somehow survives, and so the mathematical, the one terminology here is that you expect this limiting object to have some kind of Markov property. And actually, here locality is not always just in time, so it's also, so in the case of the Ising model, it was a locality in space, somehow a spatial Markov property, or space-time Markov property that you expect to have. And so one big question in probability theory is, can you classify these things? And the answer is basically no clue. Right? So nobody has any clue on how to classify these objects. at this moment, basically we're at the stage that, you know, every now and then somebody comes up with a new one, and sort of there's no overarching principle of coming up with them, except in 2 dimensions, which is very special. And so it's, you know, so at the moment it's a bit like the Archimedean solids. Right? So you have a few sort of discrete objects that you know how to describe, and they sort of sit there by themselves. But we don't really have a good way of putting them together. In 2 dimensions, this conformal invariance buys you a lot. So there's a whole, especially in physics, there's a whole field sort of called conformal field theory, which to some extent gives you a kind of classification of these things in 2 dimensions. So in 2 dimensions there is a classification, although it's typically not formulated in terms of, it's typically not formulated probabilistically. So it tends to be formulated either as theorems somehow in algebra, but there should be a probabilistic analog of these theorems. Now, one case where we also know quite a bit is 1 plus 1 dimension. So what I mean by 1 plus 1 dimension is sort of time, 1 dimension of time and 1 dimension of space, which is different from 2 dimension in the sense that if you have 1 dimension of time, 1 dimension of space, you don't expect any rotation in that, right? I mean, so rotation in space-time doesn't really make too much sense as a natural somehow operation, right? Because you don't even have the same units. So there you don't have this conformal invariance. But there are still, in some sense, there are 3 natural somehow universality classes that have been identified. And so the first one is called the Edwards-Wilkinson model. So I'm going to show you in a second examples of things in each of these classes. So the first one is called Edwards-Wilkinson, and that's the Gaussian one in some sense. So that's the one which is very easy to describe. It's completely described by Gaussian distributions. It's somehow the analog of the Brownian motion in this context. Then there's one, and that's scale invariant with these exponents 1, 2, 4. So what it means is that you have a random field or a random function or random distribution which has the property that if you scale it down by lambda and you scale space by lambda square, you scale time by lambda 4, you get the same object back. Okay, so it has some kind of self-similarity like that, and so this 1, 2, 4 corresponds to this 1, 2, 4. And of course you can always set the first one to 1, right, by convention. So then there's this Kadar-Parisi-Jen fixed point, which has been studied a lot in the last 10 years or so. That one has scaling exponents 1, 2, 3. So basically the same kind of self-similarity, but with a 3 here instead of a 4. And then there's a third universality class which we recently discovered with a postdoc of mine, which we call the Brownian castle, and I'm going to show you in a second what it looks like, and that has scaling exponents 1, 1, 2. And then one question is somehow how stable are these things? How big are their basins of attraction, right? So if you write down, you come up with some sort of local rule of how to update a function of space and time, right? Then which one of these universality classes will you expect it to belong to, right? So if you sort of zoom out, you look at what happens at large scales, do you expect it to which one of these 3 do you sort of expect it to converge to? So here's an example of what you typically see in the Edwards-Wilkinson class, right? So that's called the sometimes called solid-on-solid model, or symmetric simple exclusion also. So you have a function from the integers to the integers, and now you want to put a time evolution on that, right? So that's your space, if you want. Okay. And now I have to describe to you how it evolves in time, and the way it evolves in time is that you just sort of randomly pick one of the sites, and you look at it. If it's this one, for example, this one is a local maximum, And so if it's a local maximum, well, you flip it around, you turn it into a local minimum. Then you pick another one at random, well, this one turns out to be a local minimum, so you flip it around, you turn it into a local maximum. If you pick that one, well, it's neither local maximum nor local minimum, so you do nothing. So that gives you some evolution of these curves. And there's a theorem which now goes back to the 80s or something, which says, well, if you scale this with these exponents 1, 2, 4, then there is a limit as epsilon goes to 0, and the limit is this Edwards-Wilkinson model. It's over. So here's what the limit looks like. Okay, so that's the limit of this when you run it really fast on really large scales. And it has a number of symmetries. So it has a sort of x goes to minus x symmetry, which is obvious from the dynamic. It actually also has a t goes to minus t symmetry, and it obviously has an h goes to minus h symmetry. So it has basically all three possible reflections. And it's symmetric on all of them. Now for KPZ, a typical example of what you expect to be in that universality class are things that have some kind of lateral motion as well. So here is what is called ballistic deposition. So again, you have a function from z to z, except that this time the way I interpret this is that you have a pile of bricks, and my function is just somehow the height of the highest brick above any one site. And the way it gets updated is you sort of choose a location at random, and then you have a brick falling down. Now you choose a new location at random, you have a brick falling down, but they stick to neighbors. Right? So they don't just fall down all the way, because that would be sort of uninteresting. There would be no interaction. So what they do is they stick to neighbors like that. Right? So you have another one falls down. Here it sticks to the neighbor. Now, here already it seems sort of relatively simple model, a bit of the same type as the previous one. Here already there's no theorem. Okay, so the conjecture is that you can find a constant c, so that if you rescale it with these 1, 2, 3 exponents, it has a limit, and then the limit is supposed to be this KPZ fixed point. So let me show you what this thing looks like. So this looks like that. So here you have, these bricks piling up. And so if you kind of look at this at larger scales, it sort of looks like that. Right, so now you have these bricks piling up sort of super fast. It looks a little bit similar to what we saw in the previous simulations. Right? The difference is that, well, so first it actually moves faster, well, which you don't really see in some sense because it sort of depends on how you scale time, but time scales differently, right? In one case it's with a cube, in the other one is with a power 4. If you actually count how many steps you need to do to see the picture change, this one changes much faster. And you somehow see this kind of lateral motion, right? So what happens here is that if you have a sort of relatively high pile of bricks somewhere, then the new bricks that fall down, they all stick to the neighbors, and so that pile of bricks sort of broadens out. Right? And so that's what you see here sometimes when you see sort of large piles of bricks appearing, that you see them widening. Right? Whereas in the previous simulation here, you didn't have that mechanism. Right? So here when you have a peak, well, the peaks come up and then they come down again, but they don't sort of broaden out. But here the difference is really in the dynamic. So if you did screenshots somehow and you just look at the screenshot at fixed time, they both actually just look like a Brownian motion in X. Okay, you can't really distinguish them at very large scales. So that one still has symmetries but less. So it still has the x goes to minus x symmetry, which is clear here. It doesn't have, it has sort of neither t goes to minus t nor h goes to minus h separately, but it has it sort of together in the sense that if you take the limit, you reverse time, and you map h to minus h, then you get the same process back. But you have to do both of them at the same time. Okay, so it has kind of one symmetry less. And so then there is this Brownian castle, which we have sort of discovered recently. And so there, one construction goes like that. So here you have space horizontally, you have time vertically, so space is discrete, time is continuous. What you do is you throw down just randomly these three types of objects. So you throw down sort of dots completely randomly, and you throw down sort of arrows pointing to the right and arrows pointing to the left. And now what you do is that for any space-time point, if you want to compute the value of the function at that space-time point, what you do is you just move backwards, always following the arrows, and you count how many red dots you encounter. So here you encounter 2 of them, so the value of h at this point is 2. Here you go back, you only see 1 red dot, so the value of h at this point is 1. Okay, so you take, so that gives you a certain rule for constructing a random function of space-time. And here you can prove that actually if you scale it like this with the exponents 1, 1, 2, then it converges to a limit. And it still has some symmetry, so it does x goes to minus x and h goes to minus h, but it doesn't have any form of time reversal symmetry. So let me show you what that thing looks like. It actually looks like that. So this is what you get in the limit when you perform these rules. So here, you see one thing that you see is that it's much less flat than in the previous case, which comes from the fact that the first 2 exponents were 1 and 1, which means that the vertical scaling exponent is the same as the horizontal one. And so if you just zoom out, in the usual way, you actually get a limit. Whereas in all the other cases, the vertical exponent was 1 and the horizontal one was 2, which really means that you should zoom out in a way so that the height goes like the square root of the width, but we actually just zoomed out, in the normal way somehow, which then squashes everything down. Okay? So the fact that here you see actual order 1 size features, even when you zoom out really far, is a reflection of the fact that the first 2 scaling exponents are the same for this object. Another thing you see here is what's sort of interesting is that the limit is discontinuous. Right? It's not, so you don't get a continuous limit like in the other 2, but you get a discontinuous limit. And actually you can prove that the limiting object, it's really sort of discontinuous on a dense set of points, so it's really discontinuous pretty much everywhere. And there's a nice description of somehow how these discontinuities move. Okay, so now here's a picture. So now we have these 3 objects, right? So all these 3. So there's this KPZ fixed point, there's Edward Wilkinson, and there's this Brownian castle. So all 3 of them are somehow random functions of space-time. They all 3 have this kind of scale invariance. They all 3 have some space-time Markov property. They all 3 sort of arise as scaling limits of some kind of discrete models. Now you ask yourself, so if I take an arbitrary discrete model, which one is it sort of more likely to converge to at large scales? And Wilson, in the sort of early 70s, he came up with this sort of renormalization group picture. So what he was saying is that, so he was a theoretical physicist who got the Nobel Prize in the 80s, basically for that picture, part for that picture. So he was saying, you should really think of somehow the space of all models as an actual space, and then as the operation of zooming out as being some kind of evolution on that space. Okay? And then these scale invariant objects, they're kind of fixed points of that evolution, right? Because they are themselves invariant under the operation of zooming out. And then you can sort of, in that mental picture at least, you can imagine, now you can sort of have a dynamical systems sort of intuition. You can ask yourself, well, these fixed points, are they stable? Do they have like unstable manifolds and stable manifolds? Or, you know, sort of like the space is an infinite dimensional space. So, because, and it's not a continuous, I mean, you know, mathematically it's not completely clear what that space is. But still, you would want to have some sort of dynamical system type intuition about what happens in that space. And so what seems to be, so the current state of the intuition, at least for these 1 plus 1 dimensional, is something which is sort of summarized in this picture, which is that this KPZ fixed point is sort of the most stable of all. So if you just come up with a more or less random sort of evolution for 1 plus 1 dimensional models, chances are that, you know, it's going to converge to a KPZ fixed point if you rescale it, unless you started off with something quite symmetric. Of course, you coming up with something random might not really be random in the sense that you actually have good chances of coming up with something quite symmetric. So maybe in that sense you wouldn't necessarily converge to that, right? You may well end up with something that actually converges to that guy, which is more symmetric. So that's somehow the most symmetric one. So if you come up with something nice and symmetric, you have chances to converge to that one. Now in this picture there seems to be a kind of unstable manifold, or like a heteroclinic orbit that connects these two. So what does that mean? So it means that you can find a model which has the property that if you zoom in, right, so zooming in means going against the arrows here. So if you zoom in, it looks like this Edwards-Wilkinson model, and if you zoom out, it looks like this KPZ fixed point. And there seems to be only one such model. So this really seems to be like a heteroclinic orbit, like a one-dimensional heteroclinic orbit, which is not clear because that space is an infinite dimensional space, right? So there's a lot of space for connecting fixed points here. And that orbit is called the KPZ equation. Okay, so there's a stochastic PD called the KPZ equation, which, well, by now one has a pretty good description of it. And it has these two properties. So if you zoom in, converges to Edwards-Wilkinson. If you zoom out, at least conjecturally, converges to the KPZ fixed point, but there's very good evidence. And one has sort of pretty good mathematical evidence that it's the only object of that type. And what sort of evidence do we have? So we have the sort of theorems that we have. It's the following kind of flavor, right? So what sort of theorems can you prove here? Well, so what you do is you take a one-parameter family of models where the typical model in your one-parameter family of models, you expect it to converge to this KPZ fixed point as you zoom out. But then there would be one specific value of the parameter for which the model is sort of symmetric, and then it has to converge to this Edwards-Wilkinson. Right? So you have a one-parameter family of models where the typical model, as you zoom out, converges here, but then there's one of them that actually converges to that. And now you take some sort of simultaneous limit as you take the parameter close to the specific value for which it converges to that, but then you zoom out at just the right scale so that you see things with bifurcate. Right? And then you would want some kind of theorem that says for a very large class of models of that type, when you do that simultaneous limit, you always get the same limit. And that limit is the solution to the KPZ equation. Right? And so that sort of theorems we have now. Right? So we have like a very large class of models depending on a parameter for which something like that is actually a theorem. Right? So this is really a one-dimensional sort of heteroclinic orbit. On the other hand, this Brownian-Castle guy, so he seems to be the most unstable of all, in the sense that you perturb it in pretty much any way, you don't see it anymore. And there seems to, we have a explicit description, if you want, of a family of models that have the similar kind of property, but between this Brownian-Castle and the Edwards-Wilkinson models. So in the sense that if you zoom in, they look like this Brownian-Castle. If you zoom out, they look like Edwards-Wilkinson. But there we actually have a whole infinite dimensional family of them. Right? So here, this is not like a one-dimensional sort of heteroclinic orbit, but it's really an infinite dimensional sort of space of heteroclinics that kind of connects these two. Okay, so these behave very, very differently. It seems to be somehow a general feature of Gaussian, so this is the only Gaussian guy here. So it seems to be a general feature of Gaussian guys that the sort of unstable manifolds are finite dimensional, if you want. But it seems, and the thing is that in the physics literature, they basically did all the perturbative analysis done around the Gaussian guys. Right? So they just take it for granted that somehow the unstable manifolds are finite dimensional. Okay, so I think I'm sort of getting to the end, so I should probably stop here. Right, so there was a, well, okay, so I think I'll just stop here.
That was a great talk. I really enjoyed that, and I'm sure everybody did. We probably have time for one or two questions. Tibor.
Was there any physical motivation for this Brownian Castle model? And
no, actually, so yeah, so the motivation for that model was that actually when Giuseppe came to, well, at the time it was the Warwick to work with me, what we wanted to do is find a sort of nice family of discrete models for which we have one of these we call weak universality results. And so what we started to think about is trying to find a one-parameter family of models where somehow one endpoint in that one-parameter family of models would be ballistic deposition. And so we came up with a natural, somehow one-parameter family of models for ballistic deposition, because in some sense you can introduce a temperature, and then ballistic deposition is like the zero temperature limit. And so then this Brownian castle was the infinite temperature limit. And so we spent quite some time trying to prove that that thing converges to Edwards-Wilkinson, and didn't succeed for obvious reasons. And so then at some point we just thought, no, I mean, that's too stupid, it just doesn't work. Let me just simulate it on the computer and see what it looks like. And now because we've seen the simulation, it's clearly not Edwards-Wilkinson. And then once you somehow overcome the psychological block of trying to prove something wrong, which is wrong, right? And it's actually very easy to construct the scaling limit. So you just shouldn't try to prove that it converges to something which it doesn't converge to.
Yes.
You said that the classification of all processes has been
Could I ask you to speak very loudly?
Yeah. Would you say that the classification of all processes could be classified as the holy grail of probability theory? And what is the mathematical statement, if we have any, of classification of all processes?
Oh, okay, so here,
yes,
so in some sense, the mathematical, this is pretty much a well-defined mathematical statement, right? Because you can, so all of these properties are sort of perfectly well-defined mathematical. Okay, Markov property is somehow slightly tricky a bit because it's, okay, but still, I mean, and so then you just ask yourself, you know, how many guys do you have here of these properties? So for example, if there's no space, so if there's only time, well then there's only the stable Levy processes. Right? So there's the Brownian motion, and then there's the stable Levy processes, and that's it. And if you want to actually have finite moments, which is a pretty reasonable thing to assume, then there's only Brownian motion left. Right? So you would want to have like a higher dimensional analog of a statement like this.
Except that if I pose this question as finding the correct probability measure on a space of processes, on a space of functions, I might not be talking about the space of continuous functions. But
you might be talking about the space of distributions.
Or something like that.
That's
so
where somehow Markov property becomes a
problem.
little bit trickier to formulate.
Right.
Somehow, right? That there's like a germ Markov property.
Right.
Because they can't. Here somewhere you would also want, the thing is you want something like the something a bit analogous to the independent increment property. I mean, in the sense that I didn't really mention it here, but so So here, for example, in this 1 plus 1 dimension, you could restrict yourself. So here, all the models that I show, there are things that have the property that the way your curve evolves doesn't depend on where you are vertically, right? So if it depends on what it looks like locally, but it doesn't actually depend on where you are vertically. So we might, for example, add a constraint like that. And that becomes also a bit trickier to formulate if you're distributional. So yeah, the actual precise formulation is sort of to be discussed somehow. But the thing is that since there's no statement at all, right, if there's any statement that goes in any such direction, you know, with as many crazy constraints that you want somehow, but you know, as long as they're vaguely reasonable, that would be great already.
Any more? One more question?
With your hexagonal grid that converges to the free field, what scaling were you using?
Oh, so that would actually, so the scaling exponent for the free field is 0 in 2 dimensions, actually. So you only scale horizontally. So you just squash it horizontally and you don't scale it vertically at all.
Okay.
In 2 dimensions.
Right. But is there some other kind of scaling where you would get something like Brownian sheet, the limit?
No, the Brownian sheet is not very natural, actually. It's not rotation invariant. It doesn't have a nice kind of Markov property. It has a Markov property, but it's a strange one somehow. So it's not very natural in this context, the Brownian sheet.
So you don't get that.
So you don't get, no, you would never get the Brownian sheet as limits of things like that.
Okay, I think we should thank Martin. This is a Maxwell Institute Distinguished Lecture. We have a reception. I believe there's a reception. I hope there's a reception out here.